don't want to record to the cloud. I want to record to this computer. Did I start recording?
Yeah.
Ah. Okay, I'm having technical difficulty. All right, so hello everybody. I think majority of you are online today. We do have a few students in the class. If you're online, please make sure to turn on your video so that we can see you. So that would be good. All right, so what I want to start with first is to tell you that there is a lecture that is recorded from last year that I want you to watch on your own. At the beginning of the semester, I did tell you that we might have a couple of lectures where we have to record them and you just watch them. The reason is that the first 2-3 lectures, we were getting accustomed with this new medium of teaching and also taking some time to talk about lab in lecture. So I am behind about 2 lectures. And I wanted to start with chromatography today because next week's lab is starting your chromatography labs. So the one lecture then that I have picked from last year is already recorded. I was giving it in class last year, so you can hear students' questions, me answering students' questions, but that's all happened last year. So I posted it on Canvas. So I want to show you where it is. I want to make sure you get there. And for encouragement, I'm attaching an extra credit with this lecture. Let me put this over there. Show you where it's at. So if you go to the class here, and then modules, you will find it under week 4. This is week 4. So you will find it here. Food analysis makeup lecture, sampling and sample preparation. It's a very important lecture that talks about the importance of sampling and the preparation of samples and how to reduce error when we are sampling and preparing our samples. So this is a key lecture or key information for analysis with food or anything else, is how you pick out sample, how you get sample that is representative of the entire lot that you have. So please do listen to it, and it's part of your quizzes and part of your exam. And to just encourage you to listen and to learn the material, I'm attaching a 5 points extra credit. So how are you going to submit it? It's just summarize the lecture in about a page, not longer than a page or a paragraph even, of what you've learned from this lecture. It's like as you're studying, take notes. They don't have to be perfect notes. It's kind of an indication that you actually listen to it from beginning to end. So make sure you have notes from the beginning, from the middle, from the end, just to show that you have listen to it. It's unfortunate we have to do that, but it is what it is this semester. Everything is a little different. So please do listen to this lecture, and we will open the extra credit till Friday, 5 p.m. So by Friday, 5 p.m., make sure you submit your extra credit. That is a summary of what you've learned from that lecture. Post the notes. I mean, if you've taken notes after you listen to it, just whatever. It doesn't have to be perfect English and perfect paragraph style essay. It doesn't have to be that way. If you've taken notes the way you take notes in lecture, just take a picture of them and upload them at the extra credit. We'll have Laura make sure that she opens this extra credit. I don't know if Laura is on here, but Rachel will let her know. Okay, Good. So now we're moving on back to starting an exciting chapter, chromatography. So of course, you've potentially heard about chromatography, learned about it a little bit in different classes, but I would like to spend 3-4 lectures maybe giving you the basics of chromatography, and then we'll have specialized lectures on gas chromatography. We have 2 lectures on gas chromatography that will be given by Gary Rhinexis, who spent many years of his research where he utilized GC. So no better than Gary can cover that subject. And then I will cover HPLC, which is high performance liquid chromatography. So both GC and HPLC are forms of chromatography that are used a lot in food analysis. There's so many applications that we will talk about. We will introduce them in the chromatography chapters, but then later on in different chapters, when we talk about characterizing different components, they will come back. You will use chromatography throughout many different chapters we will be covering later on. So it is an important tool of analysis that we will be covering in class in detail. So here's where I want, there's only a few of you here, but those of you that are online, I also want to have you participate, because when I introduced chromatography at the beginning, it's a lot of talking about chromatography and seeing what you know, and then try to make it have some sense to you before going into the details of it. So what I will start by asking you, what is chromatography? Can anybody define it in like few words? What do you know about chromatography? How do you define chromatography? So those of you in class or in here, start typing something. I will put here the chat. Okay. So they can see the chat on here. I can see it. They can see the chat on their own if they want to. Okay, so separation of components in an analytical way. Separate mixture, separation of a mixture, separate molecule. Okay, so we got it. So it's basically separation. So chromatography is when you have a mixture. The first thing you want to do is you want to separate the different components in a mixture so that when we want to analyze them, we analyze them separately. We're able to detect them, identify them, and quantify them. So if we are not able to separate them, we won't be able to identify or see them or quantify them. So the first thing, the most important thing about chromatography is separating components in a mixture. Okay, so how do we do that? How do we go about doing this separation? So 2 important phases in chromatography. We call them stationary phase and mobile phase. So you have a stationary phase and you have a phase that is moving. And the components are going to interact with the stationary phase and move along with the mobile phase. So there is interaction. So in chromatography, in order to separate the components, they have to interact with the stationary phase. If they don't interact with the stationary phase, they're all going to leave a column or whatever, if it's a paper or a column. Mostly we'll be dealing with columns that are packed with stationary phase. Your components are going to just go out together if they don't interact with your stationary phase. So if they're interacting with the stationary phase, some components will interact more with the stationary phase, and some components will interact less with the stationary phase. So those that like the stationary phase, they're going to be held back, and those that don't like it as much, they're going to move along. And that's how they separate. Okay, usually I give the same story every year. Well, we have a different class every year. But I started giving that story 12 years ago when my child was very young. So now she's old, she's a college student like you. But when she was little, let's say she was 9 years old, we go to a store in the mall called Justice. I don't know if anybody knows the store. It's a lot of purple and pink stuff. So I do not like it. And she, of course, at 9 years old, loves it. So we go into the store. She starts interacting with the stuff in the store while I'm not interacting. I just go and wait by the door for her. And she's just interacting. So we got separated. She's interacting and a lot of interaction, and she won't come out of that store. How can I get her out? How would you get a child out of a store? Simple. Why do you go into the store? Does anybody type anything? Buy them something. Yes. So yes, she gets something and she walks out with it. So I can get her out of the store. Same with chromatography. So components go in, and one component doesn't want to interact, will leave very quickly, and you get separated. And then the other one takes forever because it's loving it, it's interacting with it. So that's where the role of the mobile phase come in, the phase that moves. So the mobile phase will have some substances in it that the compound that's interacting the stationary phase would like and move along with it. So I can change my mobile phase, we call it increase the strength of the mobile phase. I can increase the strength of the mobile phase to make it such that that component likes it. So then it moves faster and leaves the column. Otherwise, we can wait a whole day trying to get a compound that interacts a lot with your stationary phase. So this is chromatography, basically, separating based on the affinity to the stationary phase, and then moving them along so that the analysis is not too long, moving them along by giving the mobile phase characteristics that would allow them to, for that component to move with it. Offer her ice cream. No, that won't be a good temptation. She won't come out of the store. Okay, all right, so we can move this to the side so that I can continuously see it. And let's see, how do I bring my cursor back here? This is a challenge today. I don't know what's happening. Where is it? Here we go. All right, so the following intermolecular interactions are responsible for adsorption chromatography. So always remember, in chromatography, the compound needs to interact with the stationary phase. So in adsorption chromatography, we will learn about this, all of this. I'm just seeing if you have any idea of the type of interactions that happen: electrostatic, hydrogen bonds, or hydrophobic. Common? A and B. Okay, A and B are correct, but also C is correct. So it's really all of the above. So the interaction in adsorption chromatography can be based on charge and polarity, can be based on hydrogen bonding, can be based on hydrophobic interaction, can be based on van der Waals interaction. So all types of chemical interaction except covalent. No, we don't want it to interact covalently with our stationary phase because then it would never come up. And that is something that we don't want to happen. So the interactions are non-covalent interactions that could happen. Now, ionic exchange chromatography, we learn about it, we'll study it, but in ionic exchange chromatography, the interactions are mostly ionic based on charge. Okay, and this is one form, one specific form of adsorption chromatography. We have HIC, hydrophobic interaction chromatography. This is a specific type of adsorption chromatography that is based on hydrophobic interaction. So we have different types of adsorption chromatography. We'll learn about all of them, and we'll learn about the different types of interactions, and we'll give examples for how they are applied. Okay, so reverse phase chromatography. I don't know how much you've heard about reverse phase versus normal phase. Does anybody know? Are we answering this already? Or no, that's from before? That's from before? Oh, no. Okay. We have B, we have E. All right, let me define, so we have a mixture of answers. Let me define what's reverse phase chromatography. So we start when they started looking at chromatography, it was mostly partition chromatography. We'll learn about that in a minute. And mostly the partition chromatography, we had a stationary phase that is polar, and then we had a mobile phase that is non-polar. They call this normal phase chromatography. So when you have a stationary phase that is polar, what type of compounds will interact with the stationary phase, the polar or the non-polar? If you have a polar, common, polar. So if you have a polar stationary phase, the polar compounds are going to interact with the polar stationary phase, and they will be delayed. The non-polar compounds won't like it, will move with the mobile phase, which would be in this case non-polar. So the mobile phase will carry the non-polar or relatively non-polar compounds, and the more polar will be delayed. In reverse phase, so after they developed normal phase, they developed a reverse phase, they called it. Because then they said, okay, let's start with stationary phase that is not polar, and a mobile phase that is polar. That is the reverse of a normal phase. That's simple nomenclature because one was developed before the other. So in the reverse phase, you start with a stationary phase that is nonpolar. So your compounds that are relatively nonpolar will interact more with the stationary phase, and those that are relatively polar will move fast with the polar mobile phase. Okay, so in this case, B and C, no, it's A and C is correct. Okay, so A and C, that is F. So polar compounds elute first because they, yes, Dan? Huh? Yes. So Dan is asking what kind of situation we use reverse phase versus normal phase, and we will be giving plenty of applications later on. But if you have a mixture where most of your components are polar, right? So if you start with a reverse phase, they're all not going to separate. They're going to all go out, and you're not able to separate them very well. So you want to choose a different type of stationary phase so that you can entice some separation. And then we will definitely give a lot of examples later. So again, the answer here is A and C, which is F, okay? And this is just introductory, guys. I'm gonna go over all of the different separation modes throughout this topic. Just a historical perspective, history is great. How did chromatography start? It started early in the 20th century with David Day. He was an American geologist, separated crude petroleum using fuller earth. So that was the first use of what we know now as chromatography, but he did not label this technique, did not identify it clearly, so he didn't get credit for it. Whereas the Russian botanist Mikhail Tsvet was the first to separate pigments from leaves and used chalk for that. He packed a column with chalk and separated the different pigments and hence called it chromatography from color. Okay, so he gave the phenomena, defined it accurately and gave it a name called chromatography, and that's why he was credited for it. So in the 40s, the partition chromatography and paper chromatography came to be and to exist, and we'll talk about them in detail, what partition chromatography is, what paper chromatography is, and what's column chromatography is. And then in the 60s, there has been advancement in GC because of the petroleum industry. Separation of petroleum using gas chromatography, and over the years, gas chromatography technology went by faster and developed faster than HPLC. So it's much more developed technology, but now HPLC is picking up, or liquid chromatography is picking up really fast. So after development of gas chromatography came liquid chromatography and then supercritical fluid chromatography, and we'll talk about all of those. So that's kind of like just a brief history of chromatography. So again, can you give examples as to where we utilize chromatography? Do you know? Do you have any example that you might think of? Let's see if we have any answers here. Any application of chromatography you heard of, you think of, you know of? We got one in the chat. We're getting several. Identifying adulterants. Yes, there's going to be a whole chapter on chemicals or residues of concern where chromatography is a big part of analysis. Rancidity, not so well. If you want to determine, yes, okay. Rancidity, if you want to determine secondary metabolites of oxidation, we can use chromatography to do that. Let's see, what else? Verify composition. Composition, there's a lot of different composition you'll be doing in the lab. Next week, you will be doing something called fatty acid composition. So we look at different oils and to differentiate the oils, to detect adulteration in oil, where olive oil, for example, has gone through a lot of adulteration in the past, where other oils got mixed into it, to reduce the cost, and because olive oil is more costly than other oils. So fatty acid analysis, what's the different composition within each oil of these fatty acids? Amino acid composition is another one that you would determine by HPLC. You will be doing caffeine analysis for using the HPLC, looking at the caffeine level in different beverages. Vitamin analysis. Sugar analysis. So there's a lot of different analyses. Antibiotics, for example. Yeah, so there will be a lot of different applications that we'll be covering, a lot of that in lecture. Flavor components. Gary is the flavor master. So looking at different flavors or compounds or metabolites. Using GC to look at hexanol production, which is a secondary metabolite of oxidation. So a lot, really. Okay, so how did it all start? It started with the principle of extraction. So in extraction, it's also a separation process where you extract the component out of a mixture, and to carry on, you do that for different purposes. And we will be doing extractions in lab. One of them is actual means of analysis. So we're extracting fat from food samples to determine total fat content. So we'll use solvents, and usually extraction, you have two liquids, two different phases. Sometimes there are more phases, but in general, you have two different liquid phases, and you're separating one of the components in one phase and leaving the other components in another phase. So in fat analysis, you're using organic solvents like ether, for example, or hexane. So you can extract your sample, the fat will go into your organic solvent, and the rest of the components won't. Preliminary sample cleanup. Sometimes if you want to determine total sugars in a product, you have to dry the sample and then remove the fat, because the fat can interfere in the analysis. In order to remove the fat, you also need an extraction process. If I want to determine flavor components, for example, they're present in very, very small concentration. I want to take them out of the original matrix so that I can concentrate them and focus the analysis on them. So extraction can be done for concentration of components of interest, not just flavor, other components as well. So if we look at extraction, there are different types of extraction. There's the batch extraction, usually in the separatory funnel, which most of you might be familiar with in your chemistry labs. So where you have a separatory funnel and you have two phases that are immiscible. You have your sample, and then you would just, if you're looking for the organic phase, you would separate that organic phase and get the components in that organic phase to be analyzed. We have continuous and semi-continuous extraction. You will be doing some of that in the lab, where this is an example of a sock slit apparatus where we extract fat using a solvent. So we see here at the bottom flask, we see a solvent, and that solvent boils. We boil it, we heat it, so it evaporates, it goes up to a condenser, and then drops into the compartment where you have the sample. It solubilizes the fat, and then the organic solvent with the fat solubilized will siphon back to the original flask, and this process continues. That's why we call it a continuous or a semi-continuous extraction. And there's the countercurrent extraction, and this is the important one that led us to chromatography. So countercurrent extraction is the origin or basis for partition chromatography. So why is it called partition chromatography? Because the solutes the solutes or the components in my mixture are separating or partitioning. That means the same thing. Partitioning, that means they are partitioning between two phases. At equilibrium, a certain concentration of that component will be in one phase, and another amount or another concentration would be in the other phase. So the partition coefficient is a constant. So it is the concentration of a solute in phase one, let's say mobile phase, and then the concentration of a solute or a component in phase two, or let's say stationary phase. Okay, so that means at equilibrium, your solute or your component partition divided between two phases. Okay, if let's say your component likes phase one, it is more interacting with the phase one or the mobile phase, it will have a higher partition coefficient. If your solute likes phase two, like solute A in this example, likes phase two, which is the stationary phase, then your partition coefficient at equilibrium will be smaller. And here's an example of an apparatus that started the whole thing. We call it countercurrent extraction apparatus, that was developed with the principle of partition chromatography. Okay. So I'm going to take this and go to that link. Okay. I'm going to click on this link. Oh, so I want to take it. and show you what happens here. So this apparatus, you have multiple tubes, and the more tubes you have, the better is the separation. So the longer the tubes, the better the separation. Same with chromatography. If you have a column, the longer the column, the better is the separation. There's more time to separate based on partition coefficient. So in this case, the partition coefficient of a compound A is 0.5, which means it likes the stationary phase better. And then the partition coefficient of B is 3.5. That means it likes the mobile phase better. Let's run the simulation. So I'm going to start it here. So I have two compounds, A and B. I'm going to predict that A would like the stationary phase. So the white liquid is your stationary phase. So based on the partition coefficient, A is going to stay behind more than B. B would like the mobile phase better. It's going to move. So I'm going to illustrate by, let's say, extract and then transfer to the next tube. What happened is, in the first tube, you have less of B and more of A, and the next tube, you have the opposite. So B is moving along. Okay, so I'm going to extract, transfer. So what's happening is with every extraction and every transfer, I see separation. I see the green is separating from the red or the pink. So if I continue to do that, extract, transfer, several times moving along all of the tubes, I'm starting to see something similar to a peak or chromatographic peak that you would see in your, when you analyze your samples, you'll get a chromatographic peak. You get two peaks separated from each other. So that's basically what it is what you're seeing in these tubes. You're getting these two separated. So you want to choose a mobile phase and stationary phase that gives you two very distinct partition coefficient. Once you have a two distinct partition coefficient, you can separate them. So if we continue doing that, we get more and more separation. And then the B will leave the column, or they will leave the tubes before A. So one will leave faster than the other, and we have two peaks. And this would be in chromatography, that would be the starting time that we see the sample leaving the column, and then the highest concentration time point, and then the last time point where it actually leaves the column. So that would be in a chromatographic peak. Here we are just separating them, and we see the green are mostly here still, the red or B is mostly here, and then as we extract and move them along, we collect B, and then we start collecting A, and then we separate both of them from each other. It's pretty cool. Okay. Come back. So there are certain terminology that I'll be using throughout the next few lectures and also in lab, so I want you to know them very well. So when I say a solute, it means the component that is soluble in your starting mixture or starting solution. So you'll hear that term a lot, a solute, or your component of interest. Stationary phase, that means that phase that doesn't move, you'll hear that a lot. And that stationary phase can be a liquid or a solid, okay? And there will be cases where it is liquid and cases where it's solid, and we'll point that out as we go. The mobile phase is the phase, obviously, that is mobile, that is moving, and the sample or your solutes are moving and partitioning into or distributing, if it's not liquid, if it's solid, it will be distribution factor rather than coefficient, a partition coefficient. Partition is referred always to two liquid phases, mobile phase and stationary phase would be liquid, so we call that partition coefficient. So we can call the mobile phase, also you can hear the term eluting solvent or carrier gas or supercritical fluid. Eluting solvent, eluting is similar to when they're moving out of the column, let's say. It's called eluting, that process of leaving the column or moving along and leaving the column is called eluting. So if you have a liquid, you would hear the eluting solvent. If it is gas chromatography, we call it carrier gas. It's the same thing, it's your mobile phase, but it is your carrier gas that is inert. For example, in gas chromatography, helium is used as an inert gas. It's one type of gas that is used as an inert gas. Supercritical fluid. This is a fluid, for example, CO2 is gas. If you put it under higher pressure and temperature, above the critical pressure and temperature, it simulates a fluid, a liquid characteristics. So that is a supercritical fluid. And they're all moving, so because they're moving along, we call them mobile phase. We'll talk later on when we talk about interpreting your peaks and understanding the peaks. We'll talk about series of equilibrium. So what you want to understand here is as your solute or component going through your chromatography, it's actually going and separating between the stationary phase and the mobile phase, and then an equilibrium is reached. And this process continues throughout. There will be a series of equilibrium happening until that solute leaves the column. Eluent is your solute that is leaving, basically. Sometimes it's called eluent. So if you hear that term, it's a noun. It's referring to whatever is leaving the column. And then the verb elute is kind of actually the verb form of eluent. So elute, eluting, that means leaving the chromatography. And chromatographic peak, we will be talking about it a lot when we want to interpret. So it is the component that is coming out and being detected. As it's coming out and being detected, you're getting a measurement, whether it's an absorption measurement or kind of a conductivity measurement, depending on the detector that you have. You get a signal. At every time point, you get a signal until entire solute leaves the column. And it has this kind of the peak shape. It has this kind of a hill shape. And you'll see a lot of chromatographic peak. Some are really, really sharp and some are kind of not that sharp, depending on the chromatography column that you're using. So again, this is just defining the chromatography that we already defined. So chromatography is a separation technique. So always think separation. I'm separating my components, and in order to separate them, they have to react and interact with my stationary phase. If there's no interaction with the stationary phase, there's no separation. So, and the separation is based basically on equilibrium of partitioning and distribution. So the solute is partitioning if we have two liquids, or it's distributing if we have a liquid and a gas. For example, in gas chromatography, you have a solid covered with a thin liquid, and that's your stationary phase, and then you have the gas. So there will be distribution between the two phases. Or if you have a solid in liquid chromatography as your stationary phase and liquid as your mobile phase, then you have also distribution between adsorption on the column or adsorption on your stationary phase and moving into the mobile phase. That we call it distribution. So partitioning and distribution between stationary phase and mobile phase. So this is the coefficient, either partition coefficient or distribution coefficient, which is concentration of the solute in the mobile phase over concentration of the solute in the stationary phase. You might have them flipped in your notes, in your slides that you have on Canvas, but this is, I made it look similar to that example that I gave you earlier so that you can relate to that example. So concentration of a solute in mobile phase over the concentration of solute in stationary phase. So we have different separation techniques. So oftentimes in a quiz or a test, I ask you what would be the separation technique you would choose for fatty acid distribution of oils. You might want to say in that situation, I would use gas chromatography. So I would have, when I say what's the separation technique, you would want to tell me, is it gas chromatography, is it liquid chromatography, or separate fluid chromatography? When I say what's the mode of separation, then you have to be more specific. If it is liquid chromatography, you are going to say, oh, it's ion exchange. And more specifically, it's cation exchange versus anion exchange. We're going to talk about all of these later on. But when I say what's the separation technique, is it gas chromatography? Is it liquid chromatography? Mode of separation, then you become more specific. In liquid chromatography, we have something called planar chromatography, P-L-A-N-N-E-R, planar chromatography, or you have column chromatography. Planar because it's on a plane, basically surface. So paper chromatography or thin layer chromatography, we'll learn about these two. And the column chromatography, which is the most common and used mostly for quantification, is your column chromatography, which is more common than the planar chromatography. We spend a lot of time on column chromatography. In paper chromatography and thin layer chromatography, your two phases are liquid. So it's liquid mobile phase and it's liquid stationary phase. So when you say, but it's paper, paper is solid. Yes, because paper is your cellulose. It's kind of your inert surface where you impregnate it with water. Mostly it's water impregnation. And then they would have an organic solvent as your mobile. Thin layer chromatography, the same. You have a silica, which is very common, and then you would have your impregnated solvents. So you would have your stationary phase as liquid stationary phase, and then your mobile phase is liquid. So for planar, it's always liquid, liquid. And then when you say liquid chromatography, it really refers to the mobile phase. Gas chromatography is referring to the mobile phase being gas. And the liquid, your mobile phase is liquid. So that's kind of the differentiation there. In column chromatography, you can have a liquid stationary phase where in your column, you also pack your solid inert component, and you have a liquid that is immobilized on your solid inert phase, and then you would have your stationary phase as liquid, and then your mobile phase as liquid. Or your solid is your stationary phase, and then again, the liquid is your mobile phase. In gas chromatography, obviously gas is your liquid, gas is your mobile phase, and then your stationary phase, it used to be solid, but mostly in most recent GC, you would have your solid matrix that you have also a liquid covalently bound to it. So it becomes gas-liquid chromatography, okay? So it's basically your mobile phase is gas. Yes? On the slide, the mobile phase is listed first, correct? Yes, on the slide, your mobile phase is listed first. So gas chromatography, your mobile phase is gas. Liquid chromatography, your mobile phase is liquid. And then when we say liquid, liquid, that means mobile phase liquid, and stationary phase liquid, liquid solid, mobile phase liquid, and stationary phase solid. And so Gary will cover gas chromatography more in detail. Here I'm just giving you introductions. Okay, in chromatography, also liquid chromatography, you have size exclusion. We will learn about it, where separation is mostly or mainly on the size of the molecules. So there is no really chemical interactions. They're just separating based on size. So there's no adsorption. And then you have partition chromatography in the column liquid chromatography, where you have your inert solid covered with your stationary phase that is liquid, and then your mobile phase is liquid. And then you have adsorption chromatography, which is you have a solid stationary phase, and then you have a liquid mobile phase, and your compounds are adsorbing to the solid stationary phase. So in column chromatography, we talked about a little bit about reverse phase and normal phase. So both column and paper chromatography can be paper or planar, thin layer chromatography can be reverse phase or normal phase. We'll cover that in more detail later on. But again, reverse phase is when your stationary phase is nonpolar and mobile phase is polar. Normal phase is when you have a polar stationary phase and nonpolar mobile phase. Hydrophobic interaction chromatography, where specifically your compounds or solutes or components of interest are interacting with your stationary phase by hydrophobic interactions. Affinity, when you have very specific interactions between your column or your stationary phase and your compound. And then ion exchange, when interactions are ionic based on charge. All of these three are forms or subforms of adsorption chromatography, because you have a solid stationary phase and a liquid mobile phase, and your components are interacting via specific interactions, adsorbing via specific interactions. Okay, so hence the colors are matching the adsorption chromatography. The color of the circle is purple. So this table is very important summary table for you guys to study from, where it really summarizes the different chromatographic methods. If you have gas, liquid chromatography, what it means, and the separation is based on molecular size, polarity, and also boiling point. We'll talk about that later. So for typical fluid, what's your mobile phase, the stationary phase, and on what basis is there separation? So this is a good summary table. We will be covering all of that in detail, but this is a good summary table to know what each method is, what's the mobile phase, stationary phase of each, and how the retention means how long it stays on the stationary phase. That's the retention, how long it's retained on your stationary phase. So that means how good it's going to interact with it and on what basis it's interacting or is being delayed on the stationary phase. And these are the different characteristics that impact the retention on that. This is the last slide. I'm going to take 1 minute and then we can stop here, because you will have detailed lectures on that. In gas chromatography, your stationary phase is liquid covering a solid, and then your mobile phase is gas. So it is mostly for thermally stable volatiles. So if you have compounds that can degrade with heat, this is not the good method for it, or you have to change them to make them thermally stable. And that's what you're going to do with the fatty acids next week in the lab. You're going to derivatize them, change them chemically to make them thermally stable. And then the way it works, you have temperature gradient. So here's your carrier gas helium. It goes through to the injection port where you inject your sample. So it's carrying the different components. So the helium carries the different components and brings it into that long coily column where you have your stationary phase in there, and your component starts interacting with the stationary phase. And then here you have a gradient of temperature. Temperature is going to increase gradually, and your components are going to evaporate based on their boiling point, their polarity, their molecular weight. They're all going to contribute to the boiling point. And hence, the ones that evaporate first, they will be moving faster through the column and leaving the column and going to the detector. In this case, FID detector, because we have hydrogen gas and oxygen, flame ionization detector, so there will be flame generated. Your organic compounds go through here, they get burnt into ions, and then there will be a potential applied to it, and then you will get a change in current or change in potential directly proportional to the organic ion that got burned by the flame, or the amount of the organic ion and the type of organic ion. And that's how it gets detected. You can't hear me when I walk away. I don't know where I left you off. I'm not going to repeat. I'm sorry. So I have to let you go. Anyway, gas chromatography will be covered in more detail with Gary on Friday and Monday. Okay, I'm going to stop here. Does it say stop recording here?